Hello everybody and welcome to our review session on the area between two curves. And this is certainly a topic that we've done quite well with, and my goal is not only to try to really cover all our bases here on this topic and try to anticipate anything that the AP could throw at us, but my hope is that you can also pick up one, two, maybe three little things that are going to help you guarantee that you not just get these right most of the time, but get to that point where you just dominate this topic and get it right every single time that it shows up on an exam. And so, kind of summarize my whole message tonight. When we talk about the area between two curves, let's keep it simple. All right, let's keep it simple. I don't want to make it any harder than it has to be. For instance, we don't have any quantities being squared. We don't have any pies. All that other nonsense that we see when we start to find volume by revolution and all that. So here we go. I want to talk about vertical slices. We're going to take this region and we're going to chop it into an infinite number of really thin rectangles, okay? Emphasis on the fact that our slices are rectangles today. And what we're doing here is with vertical slices, everything's going to be in terms of x. All right, in terms of x. That's huge. All right, so the area between these two curves is going to be the integral starting at x equals a and ending when x equals b. And it is going to be the upper function minus the lower function with respect to x. And so just, if we're going to emphasize anything, it's upper minus lower. We've got to find the right bounds. Sometimes that's easier than it is. Other times we'll look at a couple where it's kind of tricky today, and that's it. Well, I believe things certainly get a little more interesting when we start dealing with horizontal slices. And so what we've got here is we're picturing that we're going to take this region and we're going to cut it into an infinite number of really thin horizontal rectangles. And here's the deal. As soon as we start mentioning horizontal slices, we're going to start to talk about putting everything in terms of y. Sometimes it'll already be set up for you, and other times we'll have to do some work and we'll have to solve that equation for x so that x is by itself and it's in terms of y. This picture, I think, says it really well. As far as integrating, we're going to start as low, okay, right here, at y equals c, and we're going to go as high as y equals d. And what we're integrating here is right minus left, so it would be the function f in terms of y minus the function g in terms of y, and of course everything's with respect to y at the end. So to kind of summarize our horizontal slices here, we're just thinking it's the right edge function minus the left edge function, and that's it. Keep it simple. Here's the first specific example that I want to get into, and conveniently I've given you not only the two functions, but I've given you this beautiful picture, and so I think you'll quickly recognize that a horizontal slice is advantageous here. If you did do vertical, it would really be a mess, especially like around x equals -2 where it's bounded on top and bottom by the same function. It would just be really, really messy, and you need multiple integrals. So here's the deal. The first thing I want to do is I want to find the y-coordinate at both of these intersection points, and you're thinking, well, I could just eyeball it. Well, usually the graph's not going to be given, and we don't want to eyeball it and assume that they intersect at nice places. So what I'm going to do is I'm going to take these two functions, and I'm going to set them equal to each other. And that's the technique we always use for finding these intersection points. So we got minus y minus 4 equals 0. What I'm going to do is I'm just going to multiply each and every term by 2 to try to kill that coefficient of 1/2. It factors really nicely. Y minus 4, quantity y plus 2. And as I tee this rascal up, we've got y equals 4 and y equals -2. And I think when you go and you look at that picture here, certainly that's what we were expecting. We had -4 as the upper, or I'm sorry, +4 is the upper intersection, and -2 is the lower. So as far as the integrating goes, I can do it all in one integral. We're going to start as low as -2. We're going to go as high as y equals 4, and it's going to be the right edge function, which in this case is y plus 1. I'm going to wrap it up, minus the left edge function, which is the red one, 1/2 y squared minus 3. And that's all with respect to y. So I think one of our biggest challenges as we move forward and try to get to that expert level is just being more comfortable doing everything in terms of y and working with these horizontal slices. Working that out we certainly are capable of integrating that term by term. It's a very friendly polynomial. First fundamental theorem allows us to plug in the upper bound and the lower bound and evaluate it numerically. Perhaps one of the AP's favorite tricks is to give you two curves that have several intersection points where you have to stop and set up a new integral. So the big key here is what happens right here at x equals c. When you have that intersection point, the linear goes from being the upper function in this region to now being the lower function in that region. And so that requires us to stop and set up a new integral. So what we're going to do is we're going to have the sum of two integrals. The first integral is going to start at x equals a and go until x equals c. And in that case, it's going to be function f, which is the linear, minus function g, which is, for today, we'll call it a cubic. All right, plus, now we've got the integral starting at x equals c and moving until x equals d. And now the upper curve is g minus the lower curve f. And we are with respect to x because everything's vertical here. So I just want to really emphasize the need for a new integral. And of course, adding two integrals is very legal here, especially this upper bound equals that lower bound. Now, I've kind of spoiled you so far by giving you pictures of the two functions ahead of time. And here's a really feisty example. F of x is a quadratic function, g of x is a cubic function, and if they wanted the area between these two curves, and this is a non-calculator question, alright, we've really got our hands full on a question like this. My first order of business is to make a beautiful sketch that is quite accurate, and that's always kind of a catch-22. You're like, alright, I want to take enough time to make it accurate, but I don't want to take so much time that, it takes me away from other questions either. Now, as far as finding the sketch, probably the most important component is getting the roots of each function, being able to factor them, identify the roots, and then just figure out, is it opening up, is it opening down, and those sorts of things. After we get that beautiful sketch going, we've got to make sure that we can clearly identify the intersection points. And those intersection points are going to turn into our bounds, of course. So that's really all, I think that's the big effort. And then once we get that done, setting up the integrals is pretty easy, as you've seen in the last couple of slides. Now, as far as these two functions go, as far as the sketch on this f of x function, we could pull out a GCF of x, and then we got negative x plus 3. So you can see that there's roots of 0 and 3. And then this other one, we not only do we have a GCF of x, and that gives us 2x squared minus x minus 5, but then it factors even more, and we could say 2x times x. And here I'm thinking, well, maybe it doesn't factor, so you make that decision. I know I've got a root at 0, and then if I really wanted the other two roots, I could go quadratic formula to solve the 2x squared minus x minus 5. But I'm going to kind of set that on the back burner and hope that I can get through the problem without really knowing that. Now, as far as this cubic, if that first coefficient's positive, then you know the cubic is traditionally going to kind of move in this way, where the left endpoint's heading towards negative infinity and the right endpoint's heading towards positive infinity. Also, the quadratic over here, because his coefficient was negative, we know that he's going to open down. Alright, so anyway, we kind of slowly put this all together, and we're going to develop a sketch that looks like this one. And getting the intersection points was really, really friendly on this one. We set the two functions equal to each other, and we got x equals negative 2 right here. We got x equals 0 here at the origin, and then x equals positive 2 up here. So the intersections were absolutely a pleasure to work with, we'll say. And I just want to clearly label this quadratic up here. Let's call him f of x. I know that yellow doesn't really show up well on the white background. And then over here we've got g of x. Whoops, I wanted that to be red. Alright, pinkish. Alright, there's our g function, is the cubic one. So as we get ready to go set this one up, I'm going to do an integral from x equals negative 2 until x equals 0. And for there, let's see, the cubic is the upper, so I'm going to go g minus f with respect to x plus the integral. And then, let's see here, now I'm going to do x equals 0 to x equals 2, and I'm going to do f of x now. The quadratic is on top minus the cubic on the bottom. And so hopefully you feel really comfortable with that setup and you can do that in your sleep. The last comment I want to make tonight is to just keep your eyes open and always be on the lookout for symmetry. A lot of times symmetry could be the difference between you getting a 4 and a 5. All right, and the reason I believe that is a lot of times I don't think the 5s know that much more calculus than the 4s. It's just the 5s know how to get to those answers more efficiently and in a quicker fashion. They're going to get the right answer in 30 seconds rather than 50 seconds. And so here's the deal. I could do two integrals. You know, I could do an integral from -1 to 0, and it looks like it would be f minus g in that region. Plus the integral from 0 to 1, and then it looks like it's g on top, f on the bottom, and so forth. But because they're both odd functions, they're both odd with respect to the origin, what I could do here in this case is just do the integral from 0 to 1, g minus f, and then double that answer, and that would represent the combined area of both regions here. So just always be on the lookout, trying to take advantage of any symmetry that may exist. On this particular example, when you're finding the area between two curves, just because it's odd, it doesn't mean the answer is 0 here. That would be, we would say 0 if we were trying to find the area underneath one curve, where the area is bounded by the curve in the x-axis, and then odd functions deliver a net area of 0, but in this case we're just doubling. Well, we're not going to spend too much time on this, but I just want to give a shout out to our polar area. We will discuss this polar area more in depth a month from now, but I just want to kind of rehash it a little bit. The difference with polar area is that we're kind of sweeping through the region like a wiper blade, where we start at this angle of theta right in here, and we say, okay, let's call that alpha. So we start with alpha, and we work counterclockwise until we get to beta up here, and basically we're breaking this region into really thin sectors. Okay, they're like really, think of like the thinnest slice of pizza you could ever cut. So it's not, there's no longer thin rectangles, they're thin sectors. And what we did is we've developed this formula that says you're going to take the radius with respect to theta, we're going to square it, and it's also, there's a half involved out there, that's the coefficient. So that's the general area for the formula for the area of a polar function, and who knows, you might see that on a near test.